All right, then I think we can start. It's a great honor and pleasure to be introducing our first keynote speaker. As the saying goes, Kevin Warwick needs no introductions, and for reasons that are at least double. Not only because his experiments gave him international recognition well beyond the academy, under the cool nickname of Captain Cyborg, for instance, or to quote one of his most famous books, I, Cyborg.
Oh, you bought that copy. Yeah.
I have it. But also because his cyborg experiments go beyond the limitations of human, all-to-human communication. And so, as chair, I find myself in a strange double bind. Either I rely on words to introduce a figure who might invite us to leave language behind, or taking the saying literally and leaving Kevin without introduction. So I'll aim for a middle way by being brief with words and using technology as a supplement. Professor Warwick is Emeritus Professor of Cybernetics at Coventry and Reading Universities. Prior to that, he was Deputy Vice Chancellor for Research at Coventry University and held various positions, including Oxford University, Newcastle University, and Warwick University. A mimetic doubling I take to be coincidental, though I found out Kevin in his youth liked reading tales of doubles like Dr. Jekyll and Mr. Hyde, or The Picture of Dorian Gray, so who knows? His experiments did lead to a double life, in a way. Trained as a chartered engineer, he's a world authority on cyborgs, artificial intelligence, robotics, and biomedical engineering, all subjects he wrote extensively about. He wrote an impressive amount of 600 papers. He has also written or edited 27 books, including bestsellers for more general readership like I, Cyborg, I mentioned, and Artificial Intelligence, I also highly recommend. All subjects he wrote about on the basis of lived experience. Kevin Warwick is in fact an experimental thinker in the Nietzschean sense, for he uses his body and thus his brain as a medium of experimentation. He's in fact known for having instigated a series of pioneering experiments involving the neurosurgical implantation of a device into his arm in order to link his nervous system directly to a computer with far-reaching therapeutic but also philosophical and existential implications. He was also successful with the first purely electronic communication experiment between the nervous system of two humans, that other human or post-human being his wife, Irena. He has given a number of TED Talks, which I've been enjoying with my wife, who all of a sudden was very grateful. I worked in a harmless field like the humanities, harmless to her physically, I mean. And here is where I need a technological supplement to give more specificity to this claim. So I would like to briefly share my screen to show you a brief clip. And tell me if you can see and hear.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralyzed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. Isn't it obvious?
I'll stop sharing my screen. And I'll just conclude by saying, I showed this clip to my children who are 8 and 11. My daughter, who is the wise one, looked on with concern as you were on the operating table. My son, on the other hand, was enthusiastic. And when he saw the robot's hand moving on the other side of the Atlantic, he blurted out, "It's supernatural." But then he immediately asked, can he still move his own arm without the internet? On that ambivalent note, welcome again, Professor Warwick. The screen is yours, and it's an honor to have you.
Thank you very much, Nidesh. Thanks for inviting me. I'll share my screen, get straight into the presentation. There we go. So hopefully you can see me and the screen. And I've called it Cyborg Experiments, as you've been describing. That's really what I'm about. This in a sense, will be a more technical talk. The cyborg, of course, is a cybernetic organism, part human, part machine, part biology, part technology, and we'll see different examples. I'm unashamedly, I'm going to talk about my own experiments. That's what I know about, and that's why if I get any difficult questions, I can answer them as best I can. There are other people who are working technically, particularly with therapy. I will talk a little bit about therapy. It's perhaps not so much the post-human side with therapy, but it is important because of the results that are achieved and so on. But I'm going to describe a bunch of experiments, all to do with cyborgs. I think myself, all of interest in the field of post-humanity, but take it as you feel. So first one. Now it's called biohacking. When I did the experiment, it wasn't. It was putting an implant in my arm. So this was a younger version of me. And it was my doctor, my GP, George Boulos. And you can see in the forceps, he's got, it's about 1 inch, like being English, I would say it's 1 inch long, 2.5 centimeters. It's a radio frequency identification device that was implanted into my left arm. And with that in place, what it did was link to the computer in my building. This is what it looks like close up. Not the thing on the left-hand side, but the thing on the right-hand side was what was implanted. Half of it, you'll see, is a coil of wire. That's where it gets its power from. It doesn't have a battery or anything like that. It gets its power from the coil. And we had in my building big coils of wire in the door frame with electric current passing through them. And if you have an implant like that and you walk through the door, current is induced in the coil. The rest of the chip a bunch of, it's a memory essentially, and you have a coded message which gets transmitted. The coil is also an aerial, an antenna, and it gets transmitted back to the coils in the door frame, which are linked to the computer. So the computer knows where you are at different times. So we got it to switch on lights when I walk down the corridor, walk towards my laboratory, the door opened automatically. You know, you have got to have a bit of fun when you're doing things like this. And coming through the front door, it said, "Hello, Professor Warwick," which was quite embarrassing when I would walk into the building sort of early in the morning with other people around, and suddenly the computer would be saying, "Hello, Professor Warwick," or I'd sort of hide away quickly. But it showed it worked. If any of you have got a cat or a dog with a chip implanted, it's exactly the same piece of technology, although they probably don't get the computer saying "hello cat" or "hello dog," but it's the same technology. So you can feel happy that it was fully tested on humans before your animal received their implant. So that was number one, the first human to have an RFID implant. The second one is what some of the students that I have are doing. Students, "Oh, yeah, can I have an implant?" And so it's not that I take students at random and put implants in them for sort of experimental purposes. It's more, we have to get ethical approval for them to carry out experimentation. And the popular one is to have magnets implanted. So is this post-human? It's an interesting question. One of the issues I have with humanity is that we have very limited range of senses. We sense the world, you know, touch, smell, sight. Sight is okay, but it's a very limited frequency range. So most of what's going on around us in the world, we just miss out on. We just don't perceive it. So we can't understand things because our senses just don't pick them up. So can we extend our senses? And this is the first one of those that I'll describe. With magnets implanted in your fingers. And you can see here, this is Jawesh, who was a master's degree student with me, and he's receiving magnets in his fingers. But you'll notice the person that's putting the magnet in, you can see he's got tattoos on his arm. And that's because he is a tattoo artist. He's not he's not a medical person. But this creates a problem because when we get ethical approval from the university, there's a line on the form which says who is carrying out the medical procedure. And this guy has a web page and he goes by the name of Dr. Evil. And so we have to say, well, it's Dr. Evil doing it, and which of course university committees don't like too much. But the students are happy with it. You can see the hand now, there's a couple, this is a left hand in case the right-handed something goes wrong. Of course, nothing's ever going to go wrong. You can see the two magnets implanted in the fingers. So what we do with it, here's Jawesh now. Now on the baseball cap, you can see ultrasonic sensors. Ultrasonics is like a bat senses the world, and it gives you a good sense of distance, a pretty accurate sense of distance in a strange way, really. But in this case, how it worked. So the ultrasonic sensors, the output is fed down to a coil of wire, which you can see wrapped around Jawesh's finger. And in the finger is the magnet. So as something gets closer, the current in the coil changes, and that vibrates the magnet in his finger. So he feels the vibrations, and pretty accurately they relate, well, very accurately, they relate to the distance to objects. So as something comes closer and closer, the vibrations increase in frequency. And because of the sensitivity in the finger, you can really feel small changes. So it's not that you have a sense of, oh, that is 2.5 meters away, and you know that 2.5 meters accurately. It's in the sense that if something moves slightly towards you or slightly away from you, you can pick out very fine movements one way or the other, and quite quickly react because it's implanted. one of my PhD students has done work on whether you implant it or you stick it on the outside of your finger. When it's implanted, you get a much faster reaction. Your brain picks up the signals much more. So it's something, you know, an experiment you could do at home if you want an experiment in posthumanity. Put a magnet in your finger and see if you can sense ultrasonic signals, see what difference it makes. I think the nice thing when you're experimenting in this field, it's very open to results from anybody. Let's see what happens and let's compare the results with what other people have got. So it's quite exciting in that scenario. Now for something a little bit different, and I'm not sure whether you're aware of this at all. Culturing neurons means growing brain cells. Neurons, of course, brain cells. Typically, we use rat brain cells, partly because the learning period in rats, they learn quite rapidly over a couple of months. And a couple of months happens to be quite nice for experiments in the laboratory. We can use human brain cells and just buy them in. Their human brain cells, quite surprisingly, end up being a little bit cheaper than rat brain cells. I've no idea why that is. Maybe it's the market for them. But human brain cells tend, as you may have noticed, tend to take a lot longer to learn. You know, you might be 20 years or 30 years. And for those of you that have students, still they haven't learned particularly well. Whereas rat brain cells learn much more quickly, over a couple of months, which is great for experiments. So there's all sorts of reasons. Rat brain cells are also quite tough, which is good if you get the students involved with what you're doing. You know, they tend to leave the brain cells out on the bench and things like that. But what we have to do is, what you see here, the top picture, you see the black rings, and then there is an array of electrodes. The black rings are really, they're called Potter rings, after a guy called Steve Potter from Georgia Tech. And what they're there for is stopping the brain cells dehydrating. We have to keep them moist. So we take the brain cells, separate them using enzymes, and then put them into these black rings, on the bottom of which, of this array, there are a bunch of electrodes linked to the gold squares that you can see. Typically, there'll be 150,000 brain cells, something like that. It's very rough, of course. And they're different shapes and sizes. Some of them are closer together. So they're not nicely structured as you would get from an artificial neural network. They're like a brain, all over the place. And some of them are bigger. The size of brain cells, a typical size would be something like 10 micrometers. So with brain, some of them get to be 20 micrometers. So they're very, very small, as you'd expect, but you're not talking nano scale. You're talking micro scale, and 10 micrometers is a typical diameter. That's just the neuron itself. You then have all the connections between the neurons. And we first have separated the neurons, and then when we put them into the dish, very quickly, you can look under the microscope, and very quickly they start pushing out tentacles in order to connect up with other neurons. So these tentacles from one neuron connect up to another neuron and become what are called the dendrites and the axons, the outputs and the inputs and so on from the brain cells. What brain cells do is communicate with each other. That's all they do, really. Each of the brain cells communicate with other brain cells. And when they get a successful connection, in some sense, then that passageway between the neurons strengthens and literally gets stronger, physically gets stronger, and even gets bigger and so on. And if you're getting a particular passageway through the brain that gets used lots and lots of times, then that passageway strengthens. So it becomes, if you stimulate one input to that passageway, almost surely the same output is going to apply or going to happen a short while later. This is formed by habit. for example, or learning in different ways. But when you do something repetitively, such as traveling the same journey to work day after day, you get to the stage where you sort of think, well, I didn't really think about what I was doing. Well, you did think about it, but a lot of it was going very quickly through your brain because you've done it so often, you don't even think deeply about, should I turn left here, should I turn right? You just sort of do it. So it is like a program in your brain, which then becomes very difficult to unlearn. But we use it here for our experiments. So after about 10 days with the brain in the little dish, as I've described it there, we give the brain a body. We link up inputs to the brain with an output. And essentially, if I describe, here's the first of the robots. The robot has technological body that you can see, and it's linked, the spinal cord, it's linked via a Bluetooth connection to the brain that we're growing in an incubator, kept at the right temperature. Now, what we wanted to do is what you've just seen, not what it's doing now. It's turning when it shouldn't be turning, and it will crash into the wall, which we don't want it to crash into the wall. All we're trying to do with this is to get the robot to detect the wall using ultrasonic sensors, stimulate the brain, which should cause it to turn right. But you can see all the change of directions is from the brain. So, and there, that one was what we wanted. Then it should have changed direction there, but it didn't. But this is like a 10-day-old brain. It's just starting off. And let's see, there we go. It's changing directions, changed its mind effectively, and then it crashes into the wall, so it got it wrong. It doesn't matter so much when it gets it wrong. What is important, there, boom, it got it right. And that particular passageway through the brain was energized. So one neuron stimulated another neuron, stimulated another neuron, until output, we picked it up and it changed direction. So every time it gets it right, great. That passageway through the brain gets stronger. It becomes more likely it's going to happen again. So all of this is quite useful for medical research. We've got a little model brain, which, as I said, typically would be a rat brain, but can be human brain cells of a smaller number, not the same size as the human brain at all. Now I'm going to skip forward. That was 10 days. Now got the same robot, the same brain, in fact, after 2 months. And you can see what happens now. So all that this robot has been doing is for about 1 hour every day, going around in this little corral, but the brain has been developing. Of course, I've chosen a good example here. I wouldn't show for a conference something that doesn't work very well. Sometimes they are a bit awkward, as you might imagine, just like a student. They don't pick up exactly what you want. But you see this one detects the wall, no problem at all, turns right. And so it goes on. And this is, it's a perfect example. The passageway through the brain is so strong that it almost always gets it right. As I say, some of them can be a bit awkward. Now, we can, rather than using a 2-dimensional structure, we can use 3-dimensional, a lattice arrangement, and that takes the number of neurons up to something like 60 million, which is quite a powerful brain. So you can have, if you wanted, you could have a 60 million human neuron brain driving a little robot around. I mean, it's a trivial example. You can get the brain to do other things, respond to noises and all sorts of things. But it's fairly limited what you can get it to do, more from experimental purpose. I mean, it could be a little walking robot, and it could learn to walk and things. If you fancy doing the experiment, if you've got a bit of money to do the experiment, you can do things like that. Sorry, but this is driving a little robot around. So it's a different form of post-humanity. We've taken the brain cells and putting them in a piece of technology, and whatever technology you want. And I think that is critical when we come later on, as to change the body. You don't have to have the body you've got. I just want to throw in a little bit of therapy. I work with surgeons at Oxford, Tipu Aziz in particular. He is a neurosurgeon using deep brain stimulation, principally for Parkinson's disease patients, but also for Tourette's syndrome, epilepsy. He would put in one in an epileptic patient every so often. Clinical depression is another use. Depends where in the brain the implants are positioned. But for Parkinson's disease, which is the one I'll describe, what the surgeon does is drill a hole down into the central area of the brain. If somebody has Parkinson's on the right and the left, then they would need two holes. And then this spindle is put down into the central area of the brain, either the subthalamic nucleus or the thalamus. Tipu doesn't use the thalamus so much. Depends on the patient to some extent, but they would have two. Now, to show how it works, and then I'll describe what we're doing and importance. So this is a guy who actually has Parkinson's disease. You can see it. He's not an actor or anything like that. You can see the muscle locking, the tremors. You see the muscle locking more when he tries to walk. Can you walk? This is with the assistant. It's very difficult to, he can't stand up because of Parkinson's disease. When eventually the assistant gets him up, so can you walk? But his feet are locked in position. His legs are locked in position because of the disease. Now he has received the type of implants that I was describing, but they're switched off at the moment. So he's got no chemical or electrical stimulation other than what's going on in his brain. You see the tremors occurring there. Now the assistant will switch on one of the power packs. So the power packs, we've got a lot of room in our chest for putting all sorts of pieces of technology, the upper chest, and that is connected underneath the skin to the implants in his brain. So you see what happens. This will be purely electronic stimulation of his brain. So you can see the effects of electronic signals. That's on the one side, switched on the left, which is dealing with the right side of his body, and then switch on the right side, which deals with the left side of his movements. And you'll see something quite remarkable then. So now it takes a few seconds to kick in. It has to work through his brain. It's stimulating the central area of his brain. It takes several seconds for that to get to the motor neural area of the brain and then down his nervous system and so on. Now he's doing the same thing that he was trying to do before, move his hand, but it's sort of, why am I doing this? Because it's not a problem. Effectively, he doesn't feel as though he's got a problem. Should I do it anymore? What's the point? It's trivial. I don't need to do anything like this. He doesn't feel as though he's got a problem. As you can see, his control of his head and walking. This is the same guy with purely electronic stimulation of his brain, that it completely changes specific types. If he can even dance if he wants to do that. So you can see and from a post-humanity point of view, the critical thing is how the human brain can be transformed by other chemicals, which I think Jekyll and Hyde was mentioned before. That was using chemical treatment. So sorry, Nidesh, to refer to Stevenson, a brilliant book. But he was using chemicals, and this is using electronic signals. What we're doing is using artificial intelligence to monitor the signals. We use the electrodes to monitor the electrical activity in the brain. That is then fed into an artificial intelligence system, which then causes the stimulation that we see just to occur when it's needed. So essentially, it's predicting, using artificial intelligence to predict from the electrical activity in the brain when the tremors are going to start, before they start, and then apply a stimulating pulse so they don't actually start. It stops them starting, if you can see what I mean. But also it can classify the type of Parkinson's disease the person's got. Electrically, they can be very different, which is quite fun as well, and it's really helpful for the surgeons. The nice thing is, if you can imagine this, The artificial intelligence system is effectively, which is a piece of technology, becomes part of that person's brain. So part of their brain is being controlled by an artificial intelligence system. Now that artificial intelligence system could be implanted into their, so it's underneath the skull, but it could easily be somewhere completely different. So what it means is, even with this technology, which is why I'm showing it, for example, part of that person's brain could be in a different city and is having an important role to play on how the brain functions. Enhancement is the last area I want to look at. And this is Nidesh showing a video before which leads on to this. So I'm doing a bit of a drum roll from that. In case some of you, and I can't imagine in a post-humanity conference, too many people thinking humans are wonderful and perfect, but some superhuman possibilities, I feel. Memory, of course, we know when in conferences, people say, hello, Kevin, how are you? And I think, who are you? I can't remember seeing you at all. And as you get older, you get that more. Why can't I outsource my memory? Why can't I, yeah, that's, I relate to that. Surely we should be able to do things like that. Senses we described before, and I'm going to talk a little bit more about that. The big one for me, though, is communication. I feel as humans, we are so poor at communicating, it's embarrassing. And by that, I mean, we've got lots of highly complex thoughts, our feelings, emotions, images, concepts, blah, 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 blah. And if we want to communicate those to somebody else, maybe a student, maybe our husband or wife, what do? Well, we convert these highly complex signals to trivial coded pressure waves. That's what this is. It's a mechanical pressure wave. And all of my complex thoughts, this is a serial signal that is very slow. It doesn't travel very far. I mean, oh, come on, surely we can do better than that. Surely we can start communicating highly complex signals directly, brain to brain. So that's the big driving force. Let's upgrade humans to something reasonable at least. Now this is Campbell Aird, lost his arm to cancer. He's been given this robot arm, but you'll see him controlling his robot arm with his human hand. Wouldn't it be better if he could control the robot arm from his own brain, as though it's his own arm? For that, we need an interface from his brain, down the nervous system, onto the wires, and back because of sensory input from the wires up to his brain. So a bidirectional interface, that's the important thing. Now, if we can do that, I'll click on this Campbell picture. If we can do that, let's assume we can have an interface, connects the nervous system to wires and back the other way. Then we can give somebody an artificial arm or artificial leg, great. But we can do a lot more. It doesn't have to be an arm or a leg. It could be a building. It could be a rocket. It could be a vehicle. It could be one of these Mars rovers that you then are controlling directly from your brain. It's part of your body, not an arm or a leg, but something different. Human brain is very adaptive. So taking on a new body form and understanding it as part of your body is not a big conceptual difference. So your body can be all over the place, but your brain is in one place and your body can, well, your brain could be in several places, for example, as well. But your brain is one place and your body can be all over the place. That's the future. The implant that Nidesh showed with the video before, that I had before, this was at the Radcliffe Hospital as well. And 2 hours operation. This was what it was. It's called the brain gate. And it was shown recently, there was, they picked up signals from a brain gate in the motor cortex and are using it now for understanding language to some extent. It's got 100 spikes. The size of it, the square size, 4 millimeters by 4 millimeters. Each of the spikes are 1.5 millimeters long. And this was fired into the nervous system in my left arm, the median nerves, which are the main bunch of nerves which go to these fingers and the thumb. They don't deal with this for some strange reason of evolution, but they do deal with these fingers here. And the surgeons opened up and fired, well, they actually had to cut away the sheath around the nerves, and then they fired this into position, and it was there for the experimentation. The electrodes, which are the important point, are about 3 micrometers in diameter. So 3 micrometers comparison to the neurons 10 micrometers typically, or nerve fibers. So you're getting a very high resolution with this implant. The neural link, the Elon Musk's neural link, is using electrodes of 20 micrometers. So they're quite big and flatter. They're not like this at all. They're not so invasive as this one. Experiments we did, ultrasonics, which I talked about a bit before. This time you can see this is me with the baseball cap on with ultrasonic sensors and a blindfold to cut out the visual. And the output from the sensors was fed down into my nervous system. So my brain was receiving signals, stimulating pulses. It took about 2 weeks to learn to accurately recognize the pulses. And then doing this was able to go for it straight away, understanding that if an object came closer, the pulses increased in frequency, and if an object went further away, the pulses died away. Interesting thing, I've said this before, but Ian, the researcher, when he just for fun, so he thought, he quickly brought that board, the green board, towards me when I wasn't expecting it. And for me, it was quite frightening. Something's coming towards me and I don't know what it is. And my brain was able to sort of react to the signals coming in. And I couldn't see what was going on, which I guess was even more scary. This is my gorgeous wife. She gets annoyed when I say gorgeous wife, but she is, so she has to put up with that definition. I think so, anyway. And she's wearing some jewellery that a student at the Royal College of Art put together. And although it had loads of technology, the student later claimed it was her piece of work. I can't understand artists, I have to say, because it was the whole team put the project together. The jewellery changes colour from blue to red. It's got light emitting diodes, LEDs, and it was linked to my nervous system. So when I was calm and relaxed, her jewellery was blue, as we see. And when I got excited, the jewellery started flashing red. Now, all's well and good. She works in a completely different office to me. If you can imagine, there she is in her office. The jewellery is blue, fine, he's not doing anything he shouldn't. And then it starts flashing red. What is he doing? And of course, who is he doing it with? So I don't think it was such a good idea, that project. This was taken at Columbia University. The guys in the computer science labs there helped put my nervous system live onto the internet. We didn't have any security. We didn't tell people what we were doing. We just went ahead and did it. And what we did was link back to the robot hand, the same one we saw with Campbell Aird. And in the video at the start, you saw a little bit of that. I moved my hand in New York, and my neural signals went across the internet to move the robot hand. What the video didn't describe is part of the experiment. The robot hand had sensors in the fingertips. This is supposed to be a robot hand now. The robot had sensors in the fingertips, and when they gripped an object, signals were sent back across the internet to stimulate my nervous system. So I was getting these pulses of current that increased the tighter the hand was gripping. What I was trying to do was to open and close my hand, which opened and closed my robot hand, just to grip an object, so just like the egg test. And that was very successful. It worked brilliantly, I have to say, that I could, my robot hand could grip an object and keep the grip there. And my brain didn't have a problem that there was this other hand that was mine. and it was a piece of technology, and it was on a different continent, and there was about 1/3 of a second delay for signals to get from my nervous system to the robot hand, and then about 1/3 back again. The brain very quickly dealt with all of that. So it does mean, no question about it, your brain can be in one place and you can have body parts where the network takes you. But the most critical thing was with my wife. She had 2 electrodes implanted, which I have to say was quite painful. I had anesthetics for my implant. Never had any pain or anything like that. But she did have, because the doctor put the very thin electrodes, pushed them in from the outside, and he essentially was looking for her to feel pain. When she felt the pain, he knew he had actually got a nervous system. So when she got 2 electrodes in, which you can see with the red connectors, we went to the laboratory and linked our nervous systems together. So every time she closed her hand, my brain effectively received a pulse. So it was a very basic telegraphic communication, Sam Morse style, ding, 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 and I would get, and back the other way. And essentially we were looking for any, if I was receiving any signals when she didn't send it, didn't close her hand, or when she did close her hand, that I definitely received the signal. So we were looking for any false positives, negatives, whichever way, but we didn't have any problems with it at all. So I think the brain gate, of course, now is being experimented on to pick up signals from a human brain and look at them in terms of communication. And I think the key experiment will be linking 2 brains together. And surely we've got the technology. It's about time that experiment is carried out. BrainGate has been used. This is not so much of posthumanity, but it gives us a sort of glimpse into that. This is Matt Nagle. He was the first one to try it after me. He had it implanted in his motor cortex. He was had a spinal injury from a car accident, but he was great taking part with the experimentation. And so when he thought about moving his hands, those signals were used to move the cursor around on the computer screen. So very quickly, effectively, you could feel, right, I'm moving my index finger, and that moved the cursor into a position. So it could switch on heating and control lighting and things like that, if you like, just by thinking about it. So his brain learnt to think in a slightly different way. And so it's going to be used for lots more therapeutic example to help paralyzed individuals. But for me, the key one is, and this is when we're looking at posthumanity, what's it all about? Well, I feel when we start communicating directly, brain to brain, just by thinking to each other, that really pushes us onto a whole new dimension. Whether we will bother trying to listen to humans still talking in this pretty awful pressure wave sense, I don't know. That's a big question, because if you're communicating by thought, it's going to be a lot richer form of communication. And it may well change, you know, what's going to happen with our faces in terms of evolution. If part of what the mouth is about is communication. If we're not using it for that sort of thing, or it's a side issue, then will that change in terms of the whole structure? I think it's a critical issue as to where we're going with posthumanity, but thought communication is the biggie. So thank you very much indeed. There we go. I'll stop sharing and hand back to you, Nidesh, to deal with any questions.
Thank you very much, Kevin, for this brilliant presentation and keynote. Such pioneering, mind-boggling, or I'm tempted to say brain-body-boggling experiments that raise all kinds of questions. So yeah, I'm sure that there will be questions. If you have a question, please place an X in the chat box, and I'll give you the word. And I see that Jenny has a question. So Jenny, go ahead.
Hi, Jenny.
Hi, Professor Warwick. Thank you so much for your presentation. It's so fascinating to hear about such experimental work, and I was particularly moved by seeing the effects of the therapy on people who had lost limbs and had Parkinson's. My question, because my research relates a lot to sort of the social implications of transhuman and posthuman technologies, I wondered if I could sort of indulge, if you'd indulge me in a question about that sort of aspect of your work. And with that, I have particularly in mind more the sections where you were talking about this kind of production of a superhuman, or a superhuman that will become a kind of next evolution of the human. And I'm particularly wondering, what do you think would be the ideal sort of socio-political system for implementing that kind of evolution, taking in mind things like kind of rich poor divides? And I asked this particularly with some of Ruha Benjamin's work on this in mind, where she talks about genome editing producing, in some of her speculative research, she talks about genome editing producing humans who would make the necessary amino acids within their bodies and therefore not need to eat. And this becoming a kind of an evolution of the superhuman compared to a human that will become much more racialized because of that human's need to engage in embodied processes of eating. I'll drop a link to that in the chat in case anyone wants to follow it up. But that's the kind of point of view that I'm interested in what you think about this sort of transhuman evolution.
Yeah, no, I think I would agree in a different sense. I mean, my thoughts are more how people would, I mean, there's questions in terms of evolution, I guess, that depends what type of evolution occurs. You know, is it a Darwinian, a pure type of evolution, or is it a more Lamarckian evolution where traits that if you start to behave in a particular way, or your body starts to operate and function in a different way, you can pass those traits onto your offspring, or not in the Darwinian sense. So it depends which. If it's a Lamarckian style, then it's a lot more quickly that it's going to happen. But I mean, I feel if you look at brain cells like to communicate. And if you give them the ability to communicate in a whole new way, then they start to change how they function. So, hey, we can communicate, we can do this, which, I mean, you can start to see that with a lot of children today, where you know, if you see a child aged about 5 or more, even younger, they don't just walk down the street anymore. They walk down with an iPhone or a cell phone in their hand, and they hardly ever look where they're going. They're just enough to get by. But the main form, the brain is doing some communication one way or another, and it's changing how they move around. And I think here, our brain cells will go for it big time. If we could now be communicating just by thinking to each other, I think our brain cells would start to function in a very different way, because to them, this is good stuff. This is what they really want to do. And hence it would change the structure of the brain. It may well enhance the number of brains. This is me speculating big time, very quickly enhance the number of brain cells we have and so on over a period of time. So I believe there would be changes of a genetic nature relatively quickly in terms of evolution. But in terms of making such a thing happen, there might be military input, but I think it's going to be big commercial benefits, because that thought communication, just looking at that, I would see it as being much bigger than, say, the development of the telegraph or the telephone, and they have completely transformed how we interact and the distance we can communicate and so on. So I think there will be commercial drivers that will, when the commerce gets into it, will change things big time, but also that there will be structures. I'm not sure whether that answers what you were looking at, but in a different way. So I think there will be structural changes in the human to accommodate the new technological abilities.
Thanks very much, Kevin. Olga has another question, and then Zegam after Olga.
Hi, thank you very much. And I already attended several years ago your lecture at Posthuman conference in New York. And I was asking question that you still don't address even in this presentation. And my question about hacking and control. And I'm not talking about government. I'm talking about a teenager next door. And of course, criminal groups. We know that hacking of hospitals right now, ransom attack, ransomware attack is very common. And to imagine like these patients that have ability to communicate with them, iron tools, iron arms could be used by international criminal groups or even by teenagers for just his own fun, to attack nurses or doctors until they get paid or until they just show up for their friends what they can do. So could you please address this hackability and controllability of these tools?
Yeah, I mean, it's a very good point. It's not my interest. Sorry if I'm not answering I will agree with you that the criminal world will see lots of advantages, new fields for criminality to occur, and different age groups, the same sort of thing. I'm sure we can look at what I think technically can happen, but it probably will be twisted and turned and used in different ways that I never imagined at the moment. So in a way, I agree with everything you're saying, but I'm a research scientist. So I look at what is possible. Can we do this? If we can achieve this or not, let's find out and let's actually do it experimentally, not just to talk about it theoretically or philosophically. Let's try and find out if we can actually get some results from this. Does it actually work? So when I talk about thought communication, it's with a belief that there will be some form of communication, exactly how it will operate, and will it be our basic thoughts or the questions, all sorts of things. But it will open up, just as with communication improvements over the years, that has opened up all sorts of issues. It's blown a hole through the privacy that people had in years gone by. Now you can listen into communication calls, you know what people are saying to each other. And it is very easy to listen to a telecommunication interaction between people. It's not great technology to do so. So it's problematic. It causes issues both for good and for bad. And I think this opens up what I've been describing, opens up, as we've seen, for therapeutic purposes, for new ways of communicating, opens up all sorts of positives, but it also opens up lots of negatives. In the military domain, you could regard it as a positive and a negative, dependent on who is the home team. If it's your friends that have got the technology, then it's all right. If it's not, then it could be a problem. So that is a positive and a negative at the same time. So I think it opens up those things. Lots of examples of that from an ethical standpoint as well, that I can go into as well, but I won't with the interest of time. So it's a very good point, but I haven't got a magic wand that can say, oh, there are no issues. But it's like nuclear power. It has big negative aspects in terms of nuclear weapons and so on.
Thanks very much, Kevin. And indeed, that's why these conversations are so important, because here you have people who work with ethics and philosophy, and you're working at the experimental level. So it's precisely the space where communication can happen. Zegam, why don't you ask your question? And you need to switch on the mic.
My apologies. Thank you very much, Kevin, for this wonderful presentation. Thank you very much, Vinitish, bringing this question of theory and ethics. And actually, it was a question I was going to ask, but you started, Kevin, to talk about this. But First of all, you say that human is poor and technology is powerful. I agree with that. And in fact, earlier I was talking, I said human is a fiction. I mean, it is a pure product of techniques and technology. Here, I would like to make a little distinction, and I wanted just to say how do you look at this? Theoretically, philosophically, we always make this distinction between techniques that is inhuman already. It can be curiosity, what Greeks call thaumazein. It could be interest. It could be a dream. Most interesting thing, if you go to Faraday Museum on Albemarle Street, what is written there? It's the person who invented electricity. I have a dream. He doesn't say I'm enough scientist. You see what I mean? And he extended his dream into sort of a huge invention of electricity. And it was very interesting for me when I went there many times. I took my students to say, look, how this engineer was playing with a word of enlightenment philosophy was emerging this particular time. And he says, but I would like to enlighten the world. You know, he was a theoretician, he was a very engineer type person, as you know. Anyway, I want to, also you said connecting the two brains, for example. Theoretically, it also exists. The first pieces of great philosophy is Plato's dialogues, which is like connecting Socrates' brain to Plato's brain. But this connection itself so technological, from speaking to writing. It's an invention of writing. And I think the key words here, again, sorry, one more word, is extension. Technology as an extension, how it was named by Marshall McLuhan. Technology is an extension of man. That was famous phrase, 1964. So that is what I was saying. What about distinction in your work, your own scientific work?
Yeah, I mean, a great fan of Faraday, and having given the
Me too.
Royal Institution, that was an enormous experience. But Faraday, I admire the guy enormously for what he was doing. And very much an experimental person, as you said. I mean, I've been inspired on the communication side. It's looking at the basics of what is communication and going through the works of Samuel Morse and Alexander Graham Bell and how they were working towards different, I'd say, technological improvements in communication. And really what I was doing was the same sort of thing. It was just messing around with the interface from the human brain onto the wires, and then from the wires into the human brain. So they did all the difficult bits, and I was just doing the interface side of things and seeing, well, if we improve the interface, then that really does have a big impact. In fact, Samuel Morse when he was talking about developing the telegraph system at the time, talked about brain-to-brain communication, which he did achieve that, except that you've got the interface problem like now. You have to use your voice or movement to press keys in order to get the signals from the brain into the computer or into the communication system. So is it an extension? This is where it becomes difficult, because if it is outside, I mean, you know, what is the brain? What are you? And if you look at the brain as a separate thing, and it's got this interface, which includes your hands and eyes and so on, if the system is outside, such as a bicycle or a loudspeaker or even a telephone, then it is an extension to you. But when it's linked directly to your brain or nervous system, then is it an extension or is it you? Is an interesting, I mean, it's as much a philosophical question. And particularly if you are linked to somebody else, you know, are you still I, or is it now we all the time? That it's not just you that's doing something. So, I mean, I don't worry too much about, well, I can't deal with this philosophically, therefore I'm not going to do experimentation. I just get on and do the experimentation and find the philosophical side of things quite interesting. So I hope what it will do is open up for philosophical questions and a new form. You know, I think a lot of the, you know, Descartes philosophy, you know, the mind and the body, and it's interesting how this then relates to that, the basic functions of Western philosophy of today. So I just see it as something which stirs it all up.
Thank you very much.
Thanks very much, Kevin. Time for some more questions. There's still some questions. We are officially at the end of the conference, but if you're available for more questions, you would like
if we could go for one more, the last one, but I'm happy if people want to email me if they've got burning questions or want to follow up, didn't like the answer that I gave. So if we could have one quick one to finish with, and then I'll...
Absolutely. Thanks very much for taking one more. So a question from Penny.
Hello, Professor. Thank you so much for this keynote. It's amazing. It's always amazing to see your keynotes and your work. I would like quickly to ask you quite a deviant question compared to the other ones. I was wondering what is the aesthetic experience and the emotional experience of the voluntary cyborg? I mean, anytime we have a body modification, this takes planning, pain. I mean, it elicits emotions and feelings. And also we have a severe change to the perceived body image of ours. So I was wondering, when we don't have a medical cyborg, and in this case, we have a voluntary cyborg, what is the aesthetic and the emotional experience? Thank you so much.
Yeah, it's a very good question. Well, firstly, let me say, I mean, when I was writing one of my books, I, Cyborg, I tried to describe the experiments, but I was describing it from a very scientific point of view, because as a scientist, you approach it, right, this is what I'm going to do, let's get all the technology ready, let's do the experiment, blah, blah, blah. And the editor was saying to me, yeah, but what was the weather like? How did the team experience this? And, well, you know, I didn't care what the weather was like. We could have been raining, it could have been snowing. That was not of any importance whatsoever. The focus was on the experiment. So that's the first thing to say, is that when you're a scientist you're completely involved. So for the implant, I was a walking laboratory for over 3 months when I had the implant in position. And myself and the team were absolutely exhausted. We didn't have a day off. We were just doing experimentation every day. But in terms of where you're heading with this, like the robot hand, when I did that experiment, do the experiment and you don't think about what it might mean or what it might, but then when I did it, I felt so powerful. It was like, you know, one of the, not like Superman, but you know what I mean? It's like you suddenly, wow, what this could mean, will mean in the future. My brain signals were controlling this robot hand on a different continent, and I could feel, and I realized, well, it doesn't have to be a hand, you know, it is part of my body. And your body image, I felt incredibly powerful. And it was pretty cool at the same time, you know, hey, I've got another hand and my brain can control it. So I was pleased with the way the technology was working, but it felt pretty cool. I have to say, when we did the experiment with my wife for communication, I have to, for me, it was like a eureka moment. The communication was that was my driving force where I came to the whole experiment from. And when that worked, I could see instantly, okay, so people are going to be able to communicate just by thinking to each other. This was the important step. And in a way, I was shocked when I then went to newspapers a few weeks later and said, this is what we've done. What do you mean by communicating like that? And I don't think some people could see the same step in the way that I did. So I was somewhat disappointed that, wow, thought communication, that didn't occur. It was, what are you talking about? And it was very difficult to describe it in a way that was more readily understood. So I don't know if that's answered the question. You really feel that the technology is part of you. Even that radio frequency identification device that I had implanted, I felt was me. So when the computer said, "Hello, Professor Warwick," yay, this is, you know, I was doing it because of me, not so because of this piece of technology.
Thank you so much.
Thanks, Penny. Thanks,
Thank
Alex.
you very much, Kevin,
Thank
for
you, Dan.
your presentation and for giving us a lot of work, actually, because these experiments are opening up so many questions about the boundaries of subjectivities. And indeed, you know, the posthuman is about these questions of breaking down boundaries between the human and technology, but having an experiment and a lived experience as a starting point provides a totally different perspective. So thank you so much for your time, for your work, for your keynote. It was a splendid closure to a very dense and full day. Thanks to all the speakers that have participated so far. It was quite intense, and we will resume the conversation tomorrow at 12:30.
Same time, same place. And yeah, rest well, everyone.
And thanks again, Kevin.
And thank you, Kevin, and all of our speakers today. It's been a very great first day, and I'm looking forward to the next 2 days.
Thank you all. Sleep well. We'll need the energy tomorrow.
Thank
Bye
you.
now.